Hello students, welcome to All Force e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with session number 102. In the previous session we have discussed heating effects of current. Few equations were derived. And in this session also we'll extend the discussion connected with the heating effects of current. Okay, so let us see what we can do today. So now let us try these two problems. And before that, let us quickly recollect what has been completed earlier. We have started in the previous session, we have started with Joule's law. It is expressed as I square RT. Heat energy produced is expressed as I square RT, where I is current passing through the load and R is the resistance of the load, and the time, is T, time for how long the current is maintained in the load. 1 kilowatt hour, this is the unit of energy, which is equal to 3.6 into 10 power 6 joules. And the electric power, it is expressed as a P is equal to VI. P is equal to I square R is equal to V square by R. Depending upon what situation we are dealing with, we have to choose appropriate form of power. If at all, if you are dealing with the combination of resistances in series, you have to go with this one. P is equal to I square R. That is suggestible because I is same in all resistances, and P can be written as directly proportional to R if resistances are connected in series. Okay, if at all, if you are dealing with parallel combination of resistances, and if you are supposed to handle power consumption in various resistances, this equation P is equal to V square by R will be useful, because V, potential difference across all resistances in parallel combination, is same. It is same. So P is inversely proportional to R in case of parallel combination. So you have to choose appropriate one depending upon what situation you are dealing with. And further, we have dealt with rise in temperature. So this is the expression for rise in temperature. Theta is written as I square rho by 2 pi square r cube k, and from this equation you can write this relation I square is directly proportional to r cube. Okay, so here rise in temperature, it depends on what it depends on what radius of the wire, provided if current is same, and if current is increased, okay, it is what, it is directly proportional to what, r cube. So I square is directly proportional to r cube. So that's the relation between I and r. If at all, if any wire melts at a particular thickness of the wire for a particular value of the current, if the thickness is increased in the sense radius is increased, for what value of current that is going to melt? If that is the question, we can make use of this relation I square directly proportional to r cube. And the next one is, in the absence of radiation loss, T is written as directly proportional to R for 4, and this T is a time in which the wire reaches to its melting point. When current is flowing in the wire, there will be heat, heat dissipation, and if there are no any radiation losses in the sense, when the current is flowing, the wire gets heated up, and when it is at high temperature, what happens? The current starts radiating energy. If at all, if it doesn't radiate energy, very quickly the wire will reach to its melting point. Okay, so this T is a time in which the wire reaches to its melting point. Under what condition this T is directly proportional to R power 4? If there are no any radiation losses. So these were the conclusions in the earlier session. So let us try to solve these two simple problems connected with that data. See this one. A fuse wire with a radius of 0.2 mm blows off with a current of 5 amps. The fuse wire of same material but of radius 0.3 mm will blow off with a current of. Regarding fuse wire, I told you yesterday, it's made up of lead and tin. Basically, it is employed in the electrical circuits, electrical gadgets to save the electrical appliances or electrical whatever circuitry elements are there in the circuit, to save them from getting damaged due to excess flow of current. We use fuse wires. Fuse wires are always connected in series. Okay, then only if a fuse wire breaks, it blows off due to heavy current flow. What happens? The rest of the gadgets, they will be safe, and this fuse wire gets damaged. Okay, so here this fuse wire, which is of high resistance and low melting point, that fuse wire radius is given as 0.2 mm. What was the radius? 0.2 mm. And it blows off with a current of 5 amp. So when a current of 5 amperes is flowing through this fuse wire, whose radius is 0.2 mm, sorry, its radius is 0.2 mm, it blows. The fuse wire of same material but of radius 0.3 mm. Now what has happened? The fuse wire's thickness is increased. If fuse wire's the thickness is increased, what happens? Radius increases, right? So if radius increases, the current at which it is going to blow will also change. It also increases, isn't it? So let us try to find out at what value of current this 0.3 mm radius fuse wire blows off. Okay, since I square is directly proportional to what? R cube, isn't it? Is directly proportional to R cube. That implies I1 by I2 is equal to R1 by R2 whole power 3 by 2. That's how you can write. And he is asking about this current I2, current at which the fuse wire blows off, whose radius is equal to 0.3 mm. So I2 can be written as I1 into R2 by R1 whole power 3 by 2. And I1 is what? 5 amps. And R2 is how much? It's 0.3 by 0.2 whole power 3 by 2. And this can be written as, you can take it like this, 3 3s are 3, 27 by 8 under root amps. So at what value of current the fuse wire blows off, whose radius is equal to 0.3 mm, 5 into under root 27 by 8 amps. For the value of current, it is going to blow off. Approximately the value will be how much? 8, so 3 under root 3, nearly something around how much? 9 amps or 8 amps. Okay, it is going to blow. Okay, now let us see the second one. A bulb of 100 watt is operating for 6 hours a day. Find the unit of energy consumed in 7 days. He is asking about unit of energy. Remember students, unit of energy is this kilowatt hour. Okay, kilowatt hour. You know, whatever power consumption is there in your houses, that is also measured in terms of units. You will, that's very often we say that how many units of current consumption is there in this month. If when the moment when you see the electrical bill, that's what you will be looking for. How many number of units of consumption we had in the last month. Okay, so what do you mean by unit of consumption? 1 unit of consumption is nothing but 1 kilowatt hour energy consumption. Okay, so here what he is asking about? He is asking about number of units of energy consumed in 7 days. It means number of kilowatt hours of energy in 7 days. How many consumption? How much energy is consumed? How many kilowatt hours of energy is consumed in 7 days? So let us find out that. We all know that power is equal to, how it can be written? Actually, it's energy by time, isn't it? That implies energy is equal to power into time, isn't it? So power, what is the power of this bulb? 100 watt into time, daily 6 hours, like that 7 days consumption we have to consider. Okay, so what you will get? You will get 6 7 0 42, 4200 watt hours of energy. And if you wanted to convert this into kilowatt hour, what you have to do? You have to multiply with kilo and divide with kilo. Then what happens? You will have something like this. So if you wanted to convert this into kilowatt hour, just divide with 1000. When you divide with 1000, what you will get? 4.2 kilowatt hour. Okay, so that's how you can handle this. So 4.2 kilowatt hours of energy consumption, or 4.2 units of energy consumption. Okay, now let us proceed ahead with further discussion. Okay, now let us talk about power consumption in resistances combination. If I consider series combination and several resistances are connected in series, and if I am interested to know in which resistance there will be more power consumption, or if resistances are connected in parallel combination, if I am interested to know in which resistance there is more power consumption, in which resistance there is less power consumption, this knowledge helps us to design what circuits more effectively. Okay, so let us try to understand that. Let few resistances are connected in series. And here I am not mentioning whether all are equal or different. Okay, they can be different, they can be equal. If they are equal, power consumption will be same in all the resistances. If they are different, in which resistance there is more power consumption? Let us try to find out. Here series combination is taken, right? So power consumption can be expressed as I square R, isn't it? Just some time before we have seen. So here in series combination, I remains constant. It is same in all the resistances. So the one whose resistance is more, in that power consumption will be more because P is directly proportional to R. So if R is large, P will be large. It means whatever electrical appliance that you have connected in series combination, if its resistance is very high, then it consumes more power. It consumes more power. So that's what conclusion we can draw. What if these resistances are connected in parallel? If resistances are connected in parallel. In case of parallel combination, potential across all the resistances remains same, isn't it? So if that is the situation, I'll pick up this equation. Power consumption is equal to V square by R. V is same and P can be written as inversely proportional to R. When you write something like this, P inversely proportional to R, what does it mean? Okay, if lesser the value of resistance that you have connected in the parallel combination, it consumes more power. It consumes more power. So when you take a parallel combination, the one which is having less resistance will consume more power. The one which is having less resistance, actually when you go with parallel combination, if one resistance is having less resistance, through that there will be more current flow. Okay, so the one which is having less resistance, it consumes more power. Okay, so that is if R is small, P will be large. Unlike in the case of series combination where if R is large, then P will be large. Here if R is small, then P will be large in parallel combination. Okay, what if, let us try to understand one more small point connected with this one. I'm going to take identical resistances. All are equal resistances only. If all are equal resistances, for example, if all are equal resistance, let all are equal resistances. If this is a situation, what is effective resistance of series combination? You can take it as RS. RS is equal to NR. If N resistances are there, each resistance is having resistance equal to R, then effective resistance of the series combination is equal to what? NR. If this is a situation, let total potential drop across all these resistances in series combination be V, then power consumption can be expressed as V square by R. V square by R, isn't it? So here, when I go with V square by RS, I have taken total resistance. If I am taking individual resistance, I cannot write V because this V is potential difference across the entire combination. When I am talking about potential difference across the entire combination, in the denominator, what I have to replace with? I have to replace with the effective resistance of the combination, unlike in this case. Okay, so here, what you can write? V square by RS is what? NR. Let us take it as equation number 1. Okay, I'll take it as PS, power combination, power consumption in series combination. So whatever those N resistances are there, if they are connected to the same source in parallel combination, then in parallel combination, the effective resistance Rp can be written as 1 by R plus 1 by R plus and so on. We will have N times, right? So what N by R is the value of 1 by Rp. Okay, so what you will have? R by N. So the effective resistance in the parallel combination of equal resistances, N equal resistances, is how much? R by N. Therefore, P subscript P, power consumption in parallel combination, is equal to V square by Rp. V square by Rp is what? R by N, or this can be written as NV square by R. Okay, this is one small, special case kind of thing. What if I consider equal resistances in series and parallel combination? Okay, so now I can write a relation between PS and Rp, right? So I'll take it as equation number 2. Let us divide 1 with 2. Then what happens? PS by P subscript P is equal to V square by NR into R by NV square. So here R gets cancelled, V square gets cancelled, you will have 1 by n square. Or what you can write, power consumption in the series combination is equal to power consumption in parallel combination divided by n square. That's how you can write the relation. Or P subscript P, power consumption in the parallel combination is equal to n square into power consumption in the series combination. So that's what the conclusion is. Let us now consider electrical appliances, like you can consider heater or bulb or any kind of let us start dealing with the bulbs. Let us start dealing with the bulbs. Well, we'll discuss about what is voltage rating, what is power rating. Okay, so what if one bulb gets fused, what happens, whether the rest of the bulbs will work or not. Okay, if they have to work, what kind of combination we have to deal with. Okay, so let us look at all these details now. Now let us deal with a special case like bulb. I will consider one electronic appliance, bulb. Whenever you purchase any electronic gadget, electronic appliance, electrical appliance, power rating and voltage rating both will be mentioned on the technical specification sheet. What do you mean by voltage rating and power rating? For example, if it was said that for a bulb, power rating is P0, voltage rating V0. What does it mean? It means if that electrical appliance is operated at a potential difference of V0, it consumes a power equal to P0. So that's what it means. It doesn't mean that you have to operate that at V0. You can operate below this potential, V0, below this voltage rating. Then also it works. But power consumption will be different. If it is operated above V0, the consequences will be chaos, chaotic consequences. The electrical appliance gets damaged because, if a voltage exceeds this one, it gets damaged. We'll see why. There will be more power consumption, there will be more current flow, and when there is a lot of current flow, what happens? There will be a lot of chances for the damage of the electrical appliance. Okay, so what does it mean? Power rating P0, voltage rating V0, in the sense if the electrical appliance is operated at V0 volts, then the power consumption will be P0. And resistance of this bulb, let us say for bulb, this is the power rating, this is the voltage rating. Resistance of that bulb is constant. Just now I told you, it's constant. And how much is irrespective of the fact that, how much current is flowing through that, what potential difference is maintained, irrespective of all these facts, the resistance of the electrical appliance remains constant. And if you wanted to find out that resistance is connected with these two values. Okay, how you can write? Resistance can be expressed as, actually power is expressed as V square by resistance, right? So resistance is equal to V0 square by P0. V0 square by P0. So that's how you can identify this resistance of the electrical appliance. Okay, so now we have got the value of resistance. Let us say a potential of V is applied across the bulb. Let a potential V is applied. Let us say that V is less than V0. Okay, if that is the situation, and if you wanted to find out power consumption, what you can write? Power consumption in this bulb, which is connected across a potential difference V, can be written as V square by R. V square by R. I'm telling you once again, this P and this P0 both are different. This P0 is the standard value, the maximum power that it can consume. Okay, at a potential V0. But right now I did not apply V0 potential. No, I have applied only V potential, which is less than V0. Let us assume like that. Okay, for this value of potential, what is the power consumption? This P. P is the power consumption. And what is the resistance of this electrical bulb? Just now we have derived it's V0 square by P0. So what you can write here? V square by V0 square into P0, isn't it? So P is what? V square by V0 square. From this equation, it is obvious that if V and V naught both are same, if applied potential is exactly equal to whatever potential he is mentioning, voltage rating V naught, then V square and V naught square gets cancelled, then P will be P naught. So if the potential applied is V naught, power consumption will be again how much? P naught. What if V is greater than V naught? If V is greater than V naught, what happens? Here power consumption will be more. V naught, V square by V naught square will be greater than 1, so P will be greater than P naught, and there will be more current flow. What does it mean? Power consumption is more in the sense there is a more current flow through that electrical bulb. So what happens? It gets damaged. Okay. So if V is greater than V naught, there will be more current flow, and the electrical appliance gets damaged. Okay, and for problem solving purpose, I want you to remember a few points. If at all, if in the question power rating and voltage rating both are mentioned, in most of the cases you need to find out the resistance. Okay, once you know the value of resistance, you can proceed ahead with the problems. Okay, and resistance can be calculated like this: V naught square by P naught. Once the resistance is known to us, rest of the things, based on whatever he is asking, we can proceed. Okay, so all that you need to do is you have to find out the standard resistance of the electrical appliance using this equation: V naught square by P naught. Okay, so let us see one small problem now. Okay, now let us try this problem. A 100-watt bulb is designed to operate on a potential difference of 230 volts. So this is the data given. So power rating is 100 watt, voltage rating is 230 volts. What is power rating? 100 watt. And voltage rating? How much? 230 watts. Okay, so these are the details given. So what he is asking us to find the resistance and the current flowing through the bulb for this default potential, and also find current drawn and power consumed by the bulb if it is connected to 200 volts supply. Okay, so instead of 230, if it is connected across 200 volt supply, how much will be the current drawn and how much will be the power consumption? So let us try to find out one by one. Resistance, just now I told you resistance is expressed like this: V naught square by P naught. And what is V naught here? It's 230 square divided by P naught is 100 watt. So 829 into 100 by 100. 100 gets cancelled. So resistance is equal to 529 ohms. The next one is current. Current I can be expressed as like this. According to Ohm's law, V naught is equal to IR, so V naught by R. R has been already calculated. V naught is given 230, so 230 by 529 amps. That's where you can live. So this is the current drawn from a potential source of 230 volts. Now, what if potential source is changed? Let us say 200 volts supply is connected. Then current drawn, you can express like this. How much is the potential? 200 divided by resistance. Resistance has been calculated. For this bulb, resistance is how much? 529. So directly you can write like this. So when you compare these two currents, here the current is less when compared to this one, because potential has been decreased. What happens if potential is is taken beyond this 230 volts? Current drawn will increase, and in that case what happens? The electrical appliance gets damaged, the bulb gets damaged. Okay, so the other thing is what? Power consumption. Power consumption can be expressed like this: I square R, isn't it? I is already known to us, 200 by 529 whole square. What is R? It's 529. So 529 gets cancelled, then you will have what? 200 square, 4 into 10 power 4 by 529 watts. So that's the power consumption. Okay. So let us proceed with the combination of bulbs. So let us deal with the series combination of bulbs. Here I have taken two bulbs. Their voltage ratings are the same, V0 and V0. Power ratings are P01 and P02. Two different power ratings are there. Okay, and these two bulbs are connected in series across a potential equal to V, and a current I is flowing. So I'm going to start with this assumption. P01 is greater than P02. It means the power rating of this first bulb is greater than power rating of the second bulb. Okay, so with this understanding, let us proceed. Uh, you know, when you take the series combination, current through the bulbs will be same. Current through the bulbs will be same. If you wanted to write expression for power consumed by these bulbs, how it can be written? Power consumed can be written as I square R, isn't it? If you are talking about power consumption in the first bulb, P1 is equal to what? I square R1. In case of second one, P2 is equal to I square R2. That's how you can write. What about resistance of the first bulb and resistance of the second bulb? You can write them here. Resistance R1, I told you in terms of power rating and voltage rating, how this resistance of the bulb can be expressed V0 square by P01, and R2 can be expressed as V0 square by P02. If you observe these two equations carefully, whatever assumptions we have made here, P01 greater than P02, that indicates that R1 is less than R2 because P01 is large when compared to P02. So R1 will be less than R2. Okay, that implies R1 is less than R2. If R1 is less than R2, P1 will be less than P2. Current will be same in the series combination, right? So if R1 is less than R2, P1 will be less than P2. P1 is what? Power consumed by the first bulb. But here the irony is the power rating of this bulb is more. P01 is greater than P02. So here one conclusion can be drawn. In series combination of bulbs, the one which is having more power rating will consume less power. The one which is having more power rating will consume less power. So that's what conclusion you can draw. It is obvious from these equations. So P1 is less than P2. That implies the bulb with high power rating will consume less power. Okay. So now let us talk about total power, effective power consumption in the series combination. Effective power consumption in series combination can be written as PS is equal to P1 plus P2. It's like total power consumption. This total power consumption can be written as total potential square divided by total resistance of the series combination. Total resistance of the series combination. Okay. Now, see, if you want, you can replace P1 and P2 with this I square R1 and I square R2 also. Again, I needs to be modified. And finally, we'll end up with this one only, V square by RS. Okay. So, PS is equal to V square by, what is the series effective resistance? R1 plus R2. Isn't it? Now, what is R1? R1 is V0 square by P01. So, V square by V0 square by P01 plus R2 is V0 square by P02. So from here, you can take out V0 square common. Then what you will have V square by V0 square into, in the denominator P02 plus P01, and whatever P01, P02 is there, it goes to the numerator. So you will have P01, P02 by P01 plus P02. So this is what power consumption in the series combination. If applied potential is equal to voltage rating, V is equal to V0. If V is equal to V0, then PS is equal to what? P01, P02 by P01 plus P02. Or you can write like this. P1 by PS is equal to 1 by P01 plus 1 by P02. Okay, so in the series combination of bulbs, the effective power consumption, okay, it resembles with parallel combination related effective resistance, where we write 1 by Rp is equal to 1 by R1 plus 1 by R2 plus and so on. So here in the series combination, okay, we are getting such kind of equation. 1 by PS is equal to 1 by P01 plus 1 by P02. Okay, so this is the expression for power consumption. What happens if, let us say, this one is having more power rating, but it is consuming less power, and this one is having less power rating, but it is consuming more power. What happens if applied potential, across this bulb exceeds V0? This bulb gets fused, it breaks, the filament breaks. then what happens? The rest of the what bulbs, they will not work. They will not work because if this here, if the filament breaks, it's like circuit is open, so there won't be any current flow, and the rest of the electrical appliances cannot be operated. Rest of the bulbs, they don't work. Okay, so these are a few conclusions connected with the series combination of bulbs. Now let us proceed with the parallel combination of bulbs. Remember, now let us proceed with the parallel combination of bulbs. I'll consider two bulbs here. Let us say this is one bulb. This is another bulb. And both are connected across a source, which is offering a potential of V. Let voltage rating of this one is V0 and power rating P01. Voltage rating V0, power rating is, for the second one P02. For the second one P02. Let current I is flowing like this. I'll assume that P01 is greater than P02. So power rating of the this bulb is greater than power rating of this bulb. Okay. So if this is the situation, let us try to first find out what the resistances are. Resistance of this bulb and resistance of this bulb. Resistance of the first bulb can be written as R1 is equal to V0 square by P01, and resistance of the second bulb R2 is equal to V0 square by P02. Since P01 is greater than P02, P01 is greater than P02, so R1 will be less than R2. Like in the previous case, R1 is less than R2, isn't it? If at all, if you are interested to find out what the actual power consumption, maybe whatever potential we have applied, that potential might be less than V0 and V0. Okay, so what is the actual power consumption? The actual power consumption can be expressed as, let us say, in the first bulb, P1, I will take it as P1. P1 is equal to V square by what R1. Since I am dealing with a parallel combination, I'll take this potential term, because potential across these two things will be same, isn't it? And what about P2? P2 is expressed as V square by R2. Since R1 is less than R2, R1 is smaller and R2 is larger, so P1 will be greater than P2. Unlike in the previous case, where if resistance is less, what power consumption is less, isn't it? But here, if resistance is less, power consumption is more. That implies if power rating is more, then power consumption is also more. That's what you can write. In series combination, if a power rating is more, power consumption will be less. In parallel combination, if power rating is more, power consumption will be more. Okay, right. So now let us proceed with the effective value of power consumption. In parallel combination, I will take effective value of power consumption as P subscript P is equal to P1 plus P2. Since voltage is a constant across both the bulbs, P1 can be replaced with this one. V square by R1 plus V square by P2 can be replaced with this one, R2. You can take out V square common, 1 by R1 plus 1 by R2. What is R1? R1 is V0 square by P01. So if you take inverse of that, what you will have? P01 by V0 square plus 1 by R2. Inverse of this one, P02 by V0 square. So finally, this is what our conclusion is going to be, P01 plus P02. So this is power consumption in the parallel combination. Now see, if applied potential is equal to voltage rating, then what happens? Pp is equal to parallel combination related to total power consumption is equal to sum of individual power ratings, P01 plus P02. And here, unlike in the case of series combination, if one bulb fuses, if it gets damaged, the other things, they stay intact, they still, work. Okay. So in series combination, if value of resistance is less, power consumption will be less. And whereas in parallel combination, if resistance value is less, power consumption will be more. In terms of power rating, in series combination, the one which is having more power rating will consume less power, and here the one which is having more power rating will consume more power in parallel combination. So these are the points that you should remember. Okay, so this is where I'll close the session, and in the next session we'll deal with a few problems connected with bulbs and overall heating effects of current. Okay, thank you students.